in having an incredible depth of research and scholarship among our grad student and faculty population. And this is an opportunity to take a look at some of these areas of research in a little more detail than one normally gets. I often think we don't do enough at Waterloo to get together and celebrate the research activities that we have going on. Today's session is going to be presented by Dr. Linda Nazar. Linda is a Canada Research Chair in Solid State Materials. She's an excellent example of the innovative research that goes on at the University of Waterloo that has both international recognition and international impact. It's the type of research that probably influences the future direction of how we deal with energy and has implications that go far beyond anything within the specific university research community, but out to the broader community. Linda is a professor in the Department of Chemistry. She's also cross-appointed to the Departments of Chemical Engineering, Computer and Electrical Engineering, and the Department of Physics. I asked her, are there any departments she's not cross-appointed to, and she said biology, but may have to fix that. She also established the Laboratory for Electrochemical Energy Materials and contributed very greatly to building the Waterloo Institute for Nanotechnology. Linda was educated at the University of British Columbia and the University of Toronto, received her honors undergraduate degree in chemistry and her PhD in materials chemistry. I think throughout her career, Linda has achieved very high standards in research and outreach to the broader community, particularly in the areas of solid state chemistry, electrochemistry, energy storage, and materials science. I also think it's fair to say that Linda is probably one of the best recognized and honored colleagues we have at the University of Waterloo in terms of the number of awards that she's received. She has over 250 publications, 8 patents, and more than 300 international conference papers. She is very active on the speaking circuit and has given over 150 seminars around the world. She is the recipient of many honors, International Electrochemistry Society awards and prestigious recognitions, including the Thomson Reuters Highly Cited Researcher list for 2016 and 2014, and in 2014 she was recognized as one of the world's most influential scientists by the same group. She was elected as a Fellow of the Royal Society of Canada in 2012, and she was named as an Officer of the Order of Canada in 2015, and has received the title University Professor from the University of Waterloo in 2016 for her outstanding work in solid-state energy materials and advanced battery research. I think I probably have said enough. Linda, the floor is yours.
Well, first of all, I'd like to thank the university for inviting me to give this talk. It's really a nice opportunity, I think, and you're quite right. We should have more events like this because I want to hear about other faculty's research as well. I'd like to especially thank you all for coming. I see some chemists in the audience, John Paradin, so it's a real delight. I actually took out some of the chemistry from the talk for fear of boring those non-chemists, so there's kind of a sprinkling of things. So what I typically forget to do is thank my research team. They are actually thanked at the end, but just in case I forget to thank them, there they are in the corner, and especially our funding agencies, BASF and CERC, Joint Center for Energy Storage Research, which is a DOE hub at Argonne. And these are the people that, this is sort of an old picture, about a year old, but these are many of the people that have done the work that I'll be talking about today, so my hearty thanks to them. There's only a couple in the audience because I told them to stay away. I didn't want them to have to keep me honest. So today's agenda, I'm going to be talking about where we're going from lithium-ion batteries. I'll be talking about storing ions and electrons in what are called chemical transformation batteries, which are more akin to lead-acid batteries than they are akin to the batteries that we have on our laptops. And then I will be talking a little bit about intercalation systems, which is the chemistry that governs today's batteries, before finally concluding. So I'll start off with the obligatory slide. about sustainable energy, but this isn't obligatory. This is actually quite important. So, Mother Earth has learned how to store energy in fossil fuels by basically the sun beating down, making plants, which then turn into biomass and produce petroleum, which we then, use. And of course, today's environment, we're looking more into renewable energies. This can be pumped water, the sun, of course, geothermal, wind, a variety of different sources. But when you look at all these different sources, the sun still really wins out when you compare it with all of these other possibilities. And the fact is that we need to go to an energy consumption of about 16 terawatts today, up to what is predicted to be needed of 28 terawatts in 2030. There's lots of seats down front, just wander down. So clearly we have to harness these renewable energies. And so arguably, energy storage is a challenge of the 21st century. It's probably more important now than it ever has been because we're moving away from our laptops into much more divergent demands. So these occur at different energy scales. In other words, we have to store at different levels. So for wind and solar, we're storing at the megawatt hour level. For smart energy delivery, whether that's powering the internet, big computing, small devices, whatever, that can vary depending on what is actually being utilized. And of course, for high-range electric vehicles, this just shows an electric bus in South Africa, we need to store pretty much at the kilowatt-hour level. So the take-home message here is that this represents many, many diverse energy needs. And it also means that we have to employ different materials, and we also have to be aware of the fact that these all have a different cost point. So what is appropriate for your laptop is not necessarily appropriate for the grid in terms of that cost. But they all have underpinning this common theme, which is they're taking chemical energy to electrical energy, and the thermodynamics drives that forward downhill effectively. That is the usual discharge process of the cell. And then we have to go thermodynamically uphill on charge to convert that electrical energy back to chemical energy. And the question is, how do we do that efficiently with new materials and new systems? What you may also not be aware of is the fact that the Global Energy Assessment Group, this came out of Cambridge in 2012, has identified integrated energy storage as an energy where technology lacks and intense development needs to be made in order to optimize systems. And this is not just electrochemical energy storage, but energy storage as a whole. And this, of course, is, I think, pretty clear to all. And they've identified 41 pathways to provide sustainable energy where energy storage, and especially electrochemical, as I said, is the real criteria. Okay, so just a little bit of battery 101. So the first thing is that whenever I'm at parties, which is not very often, people often say, why haven't you guys made a better battery? What's wrong with you? And it's waiting for this for a long time. The fact is we actually have. So what you see here is a plot of gravimetric energy density versus volumetric energy density, and this is from Sony. And I'll just explain what these are. So the capacity is basically the electrons stored per mass. We call it coulombs per gram. It has the unit of milliamp hours, but it's effectively coulombs per gram. So this is the capacity per gram, and this is the capacity per liter. So we need, in order to optimize both of them, we need both lightweight and dense materials. And of course, that can't happen, so you have to sort of have a compromise there. So the product of capacity and the voltage at which those electrons are stored is the energy density. And that's expressed in watt hours per gram, per kilogram, or watt hours per liter, which is plotted here. So you can see from this graph that we're going sort of down here in 1994. There have actually been pretty significant gains made all the way up to 2014. We're leveling off here. That's part of the problem. But we have made gains, and people haven't recognized them because their devices are becoming more and more power hungry as everything improves with the actual technology. So where do we go from here? So the problem is that the periodic table effectively limits us to about 280 watt hours per kilogram. That's this gravimetric density, based on the classic intercalation chemistry that, as I said, governs the batteries in our laptops. And there's also real problems with cost and safety. Safety is obviously a problem for the Dreamliner, for example. And cost is a factor for things such as this car, which happens to be a Tesla. It's just any old car, really. This is a particularly good one because it accelerates in 4.4 seconds to 60 miles per hour, which is better than a Ferrari. But if you compare the cost of the battery for this Tesla with some of the other less powerful versions of electric vehicles, you see that the cost of the battery is a significant portion of the car. So it's not so much that we need even better batteries, we just need less expensive ones, but ideally better as well. So the battery that powers the Tesla is based on, as I said, this process, this concept of intercalation chemistry, which was effectively started in about 1990, when a very seminal chemist, John Goodenough, worked with other scientists to develop this, what's called a dual intercalation system. So you're probably hopefully watching the cartoon. What you see is what's going on the left and the voltage curve shown on the right. So it's voltage versus basically electrons that we're putting into the system. So the short, simple answer is that, or point is that as the battery is charged, lithium is put into the graphite carbon, and as it is discharged, the lithium goes into the lithium metal oxide, which was originally a cobalt oxide, but it now has a range of nickel and manganese in it to optimize the system. So the lithium ions shuttle on charge from the carbon back to the layered oxide on discharge, and the electrons, as one plugs it into the system, the electrons, of course, are being driven thermodynamically downhill in this process, and they pass through the external circuit and do the work on your laptop or whatever else it is needed. So currently, the positive electrode has a specific capacity of about 180 milliamp hours per gram, and it stores this at a voltage of 3.9 volts. And then when you do all your little calculations at the energy, this comes out to about this value for the gravimetric energy density. And by the time you actually get into a real pack, and this is a real pack from a Tesla car, that value has dropped dramatically because of all the pack components. So then the question is, where do we go from here? Understanding that we have to optimize the energy density of the cell because it's already being diminished as we put it into the pack. So this is the Sony cell I just told you about. There's been a plethora of different materials developed over the years. I won't go through all of them. In fact, I'm going to mention very few of them. But just suffice it to say that some of them have found their ways into electric vehicles, such as the MEV, this lithium iron phosphate material. Some of them are being employed, this as well, by Hydro-Quebec to store energy from the grid. Others are used for marine vehicles. Obviously, we still need portable devices. And increasingly, robotics is becoming a real demand area because nobody wants a plug-in robot. It basically has to function with a very safe cell. So this is where the future development is hopefully going, or we were predicting it to go, and I'll be spending most of my time actually talking about this in the seminar. So at this point, I want to mention that a lot of the work that has been basically driven the field since 1990 is because portable devices have driven the market. And for the grid, even though I'm sure we're all familiar with the Tesla home battery, lithium ion really isn't necessary. There are other technologies that are cheaper, that are maybe not more efficient, but they're certainly less expensive. And there's been a variety of these explored just in the last few years. The most famous of which is the sodium sulfur cells, which actually operate at very high temperature, 350 degrees. And a company called NGK has these installed near Tsukuba, Japan. They had a fire a few years ago, but they've managed to recuperate. This is, of course, not ideal because of corrosion problems and the temperature. Vanadium redox flow batteries have become quite popular. They've been sort of creeping along for a long time. They have issues with membranes. And there's been some interesting startups, companies such as Aqueon Energy, which has developed an aqueous sodium ion cell. So these sorts of cells can be used either for home batteries, which we call mini-grid, or even for large scale. And they will probably not in the future be lithium ion. So I'll be talking about those at the very end. I'll be sort of starting ones that are intermediate because sodium ion can be used for both grid storage and for higher energy storage as well, better volumetric storage. So if the lithium ion batteries all go into the electric vehicles, which is predicted to happen over some period of time, that will effectively drive up the cost of lithium, and this is unquestionable. Now, there have been some articles, for example, in the Wall Street Journal a few years ago. They talked about peak lithium being akin to peak oil, and Bolivia, which is where most of the easily mined lithium resources has been described as the Saudi Arabia of lithium. And the fact is that it's not really that much of a concern, except when, as I said, the price of lithium starts to go up, and it certainly will. So, for example, sodium is obviously a very inexpensive and abundant element. It only has a 0.3 volt penalty versus lithium and a slightly higher mass. And the voltage really isn't so much a concern. The higher mass certainly is a concern if one is not a concern if one is going to do stationary storage. And this is only something known to electrochemists, but copper current collectors are actually pretty expensive, whereas aluminum is not, and sodium can be used with aluminum. So a lot of these concepts are summarized in this review article, and I'll just tell you a little bit about going what I call below lithium ion as opposed to beyond. So this paper came out a few years ago in Nature Materials, and it reported a new material, which is an iron manganese oxide with sodium. So this now may hopefully seem a little familiar to what I just told you about with the lithium cobalt oxide. The advantage is it only has earth-abundant elements, sodium, iron, and manganese, and that makes it very nicely low cost. And this material actually has an energy density that is comparable to many lithium-ion batteries, such as lithium iron phosphate. The problem is that it has very severe capacity fading. And so I'm not going to go through all of the details, but just to tell you, sort of summarize, that understanding what the problem is three-quarters of the challenge and three-quarters of the way there to getting to a real cell. So for example, our paper just last year showed that in a typical iron manganese oxide, as you charge the cell, the iron in particular shuffles into these interlayer sites, which happen to be tetrahedral iron coordination as opposed to the octahedral that they prefer in the layers. And this rearranged material is very detrimental because once the iron nestles its way into these little tetrahedral sites, it doesn't want to come back out. And that turns out to be serious. That's one of the major reasons for this capacity fading in these cells. So by introducing nickel into the system and affecting the way that the bonding actually occurs, we can mitigate this amount of movement, of migration of the iron, to 3% from about 12% and obtain much more stable systems. And this analysis was all done by fairly complicated X-ray diffraction, which I won't get into. So what's a little simpler then to point out is, well, if sodium is so great, why aren't people using more of it? And it turns out that it's, as I said, a larger ion, but that's not actually a problem either. So this is lithium iron phosphate, which is in most of the power tools that you buy today. And the barrier for lithium ion transport down these tunnels, this is the lithium ion here in green, and this is the iron and the phosphate shown in yellow here. So the barrier for moving lithium down these tunnels is about 0.62 electron volts. Those estimates vary according to the theoretician who does the calculations. But using the same theoretician, this is a colleague of mine, Saiful Islam at the University of Bath, we were able to calculate for this layered sodium iron phosphate an energy barrier that's about half that of the other system. And that is mostly because lithium, being a small and fairly highly charged ion, basically dives into these deep potential wells in the structure and has to surmount the activation energy in order to migrate through the lattice. Whereas sodium, being larger, has actually less electrostatic attraction, and so therefore it can sort of bump its way through the lattice a little more readily. And so it turns out that this diffusion coefficient that we calculate from this energy barrier is actually equal to lithium cobalt oxide. So that's a good thing. What's even a better thing is that computational science has really dramatically changed in the last even 5 years. And there is a materials genome project underway in the US. It's mostly housed now at Berkeley because of the people that have moved, but this is accelerating the design of new materials. And the short version of this is that they have calculated many new materials that are potentially quite interesting. And right now, 200 new ternary compounds. This is really accelerating. Most of this work is being carried out by Gerhard Zeder and Kristen Persson. So we have a lot of new materials starting to come out on the horizon, and one of the difficult things is to figure out how to actually make them. It's one thing to compute them on a computer, but it's quite another to actually prepare the materials. And so here's one that my postdoc, who's actually sitting at the back of the room, Deepan Kundu and Rajesh Tripathi made. And they actually did this with a pencil and paper, no computer. And then they actually went in the lab and prepared it. So it has also a very similar low activation energy. Computation turns out basically the same activation energy for transport. And the sodium moves through these little wiggly or wavy green pathways that are shown here. And this material has a very high voltage, which makes it inappropriate for any organic electrolyte that's used in these cells. However, it has a really high energy density just for the cathode. And so we have been struggling for some time to try to make this battery, this cathode, this positive electrode material work in a solid state cell, because it has all the right qualifications. And solid state batteries are another one of these hot topics. This is from, again, this in this case is Toyota, and this is their roadmap from 2014. And it just shows energy density down here, power density on the other axis. And it shows sort of where we've come with lithium ions. And this is where the holy grail is, the lithium air battery. And in between, they believe that the all solid state battery is the answer to the problem. And mostly in part for safety. So what we have been exploring for some time, we're still not there yet, is a solid state battery which employs this material that I just described in the previous slide with a well-known sodium ion conductor, which is a solid, and some other sodium intercalation compound of the negative electrode into one entire cell. So the way these solid state batteries are built, as you just sort of saw, is that we have a solid state electrolyte, and that means that we have to have good ion conductivity in that material. And then that electrolyte effectively is interwoven with the negative electrode and the positive electrode into one seamless, interface-free system. And that's, of course, the ideal. It's very hard to get there. So we need certain properties for the electrolyte. We also need the positive and negative electrode materials to conduct electrons, and that usually means adding additional material. And so this all becomes a real issue of interfaces. And if anyone is a budding or experienced surface scientist, there is an awful lot of hay to be made in this area. And the advantage of solid state batteries is just that because they have a solid electrolyte, there is no organic electrolyte to catch flame. There's a reduction in packaging because you can now assemble these into thin films, stacked thin films very readily. And finally, they have very long cycle life and no self-discharge because, again, there's no organic electrolyte in the cell. Now, I'm making this sound like it's really simple, and in fact, it really isn't. They're just starting to come out in the marketplace. So predictive capability, of course, is the key to accelerating the innovation cycle. And if you take a look at some materials that have been developed over the years, Teflon, Velcro, diamond films, you see that basically there's about an average of 2 decades from commercialization to realization. So, these things aren't going to necessarily happen tomorrow. They really do take a while to sort out. So the other new system sort of on the frontier does not rely on intercalation, but it relies on a chemical transformation. And there's 2 kinds of cells which are based on chalcogenides, those elements underneath oxygen. So really sulfur is the chalcogenide, oxygen isn't, but close enough. And they are the lithium sulfur and lithium oxygen cell. So obviously the lithium oxygen cell uses oxygen, and it simply reduces the oxygen to lithium peroxide by the incorporation of 2 electrons, and of course lithium comes along for the ride, and that happens at about 3 volts with a pretty high energy density. The sulfur cell, on the other hand, is at a slightly lower potential. I've put this as a 2-electron reduction as well. These are obviously reversible couples. And sulfur, just like oxygen, is very inexpensive. In fact, it's $150 a metric ton. And so this chemistry is motivated partly by the cost and partly by the fact that there's some really new chemistry here that really has many potential opportunities for commercialization. So when we compare these cells to the classic metal oxide chemistry that I showed you at the outset, we have those cells typically would be about 200 watt-hours per kilogram. We have a factor of about 3 that is possible with the lithium sulfur cell and even more with the lithium air cell. So it's cost and energy density. So why aren't we there yet? Well, there's just a whole host of problems. So I'll just tell you a little bit about our research in the lithium air business. This redox couple, again, is that reduction of oxygen, and it forms an intermediate, which is effectively lithium superoxide. And 2 lithium superoxide find their way together in solution in the electrolyte to form lithium peroxide and release oxygen, which then comes back and sort of reacts. So the problems really are partly the reactivity of that superoxide. The good news is that there is basically a minimal overpotential for oxygen reduction in this system. And that is because, unlike a fuel cell, where you all probably know that you need these expensive platinum catalysts to do the chemistry, we are not breaking the oxygen-oxygen bond. It remains intact in lithium peroxide. All it does is stretch out a little bit. So we don't need electrocatalysts for this reaction. In fact, it's remarkably facile. And that means we don't have to pump up. There's no kinetic overpotential associated with the reaction. The problems, however, are reactivity of the electrode with the peroxide, and that means we need a nanoporous, metallic, highly conductive, and stable host material. And the other problems are the organic electrolyte, because it reacts with the superoxide, at least the electrolytes we have now. And there's also the simultaneous challenge of finding electrolytes that will solubilize oxygen, which is hydrophobic, and solubilize salts, which of course are hydrophilic, while being stable. So this is just a little diagram from our review article that shows all of these problems that we're all working on: the stability of the electrolyte, the transport of electrons, because the peroxide is an extremely good insulator, and also cathode stability. So obviously I'm not going to have time to tell you about these. I'll just show some overhead from some of our recent work. This is from work from Deepan Kundu and my previous grad student, Robert Black, who's now gone on to a position in industry. So the short story here is that we have learned, for example, how to control the reactivity with the cathode host in which the oxygen diffuses and deposits its peroxide. And the short story is that this reaction is fairly reversible. In other words, it goes in this direction and back in this direction, as long as we don't have irreversible reactivity with that host. And that means no carbon, because it forms lithium carbonate. So control of the interface is absolutely paramount. So we've used a metallic oxide, which is called a Magnelli phase, and these are little tiny particles of that electrode. And you can see that upon discharge of the cell where we form the peroxide, we see platelets of peroxide literally crystallizing from solution. And they do this because two of these superoxide molecules simply get together, they nucleate, and they're fairly insoluble, and so they crystallize out into these beautiful plate-like shapes. And when we charge the cell, you can see that the electrode is completely devoid of the peroxide. So it really is quite reversible if you do things right. That's not to say that we've solved all the problems, but we're certainly understanding things better. This is also a diagram from our review article that simply says that we now understand, for example, that rather than binding the superoxide to the electrode surface where it forms these amorphous non-conducting films, we really need to get it off the surface so that it crystallizes to form these peroxide particles. So if it doesn't bind closely to the surface, it wafts off to form the peroxide, which then crystallizes as these large aggregates. And so this can be tuned with solvation, with the kind of electrolyte, and it can also be tuned with current density, and we've published a bunch of papers on that. And then also recently we've turned our attention to the sodium oxygen system, partly because it's, not because it's necessarily more higher energy density, because in fact it's lower, but it stops at the sodium superoxide. It doesn't move all the way to the peroxide, and that's for reasons of thermodynamics. Now, we did not develop this battery. This was actually invented in 2012 by a group in Germany, Jürgen Janek's group. But what we did do was understand how these massive tens of micron size cubes ended up littering the surface of this electrode surface, and then miraculously managed to reoxidize in the process, considering, again, they are pretty much perfect insulators. And so the short answer to this is in our Nature Chemistry article, which shows that the oxygen that is reduced to superoxide actually picks off any proton that's always there in the solvent as a trace, because there's always a little water in the organic electrolytes, they're never perfectly dry, and it forms this hydroperoxy radical, which then undergoes metathesis with sodium to literally nucleate these large cubes. And exactly the reverse process occurs in charge. It undergoes metathesis, the hydroperoxy radical takes that superoxide to the surface and releases it as oxygen. And so these cells have actually a very low overpotential because of this phase transfer-driven catalyst. So we collaborated with Jonathan Bao to understand this a little bit better. We actually did sort of quasi-in situ cells where we have obviously this is done in the absence of air and moisture. So we have an electrolyte, we pump out a bit of electrolyte, we cool it immediately at 210 K in the presence of a spin trap, which is called DMPO. Its structure is shown here, but that's not important. And then we immediately pop that into Jonathan's ESR spectrometer. And we see, first of all, with a little low contents of water, we see a classic spectroscopic signature of the hydroperoxy radical. But as we add more and more water into the system, and 5,000 ppm isn't really very much, you see the appearance of a second set of signals. And those are just shown here if anyone happens to like ESR spectroscopy. And so we can see the difference between 10 ppm at 100 minutes charge versus 500 ppm. And the point there is that that purple or magenta spectroscopic signature is a classic of carbon-based radical systems. And this is the organic electrolyte, the glime, that we are actually using as our solvent in the system. So the short story is that the superoxide is attacking this glime, picking off this proton as well, and it's actually the hydroperoxy radical that is doing this. So we need to find, we're the first to actually show the evidence of these radicals, and so now we need to find electrolytes that are stable to hydroperoxy abstraction. And this is really difficult because these are the same guys that are responsible for aging in the human body. And so we're hoping to do this to the battery someday soon with the right electrolyte. Let's go down the periodic table and move down the chalcogenides. So sulfur batteries are a little bit different because we have a solid to start with. And so back in 2009, we were approached by Toyota and we said, well, let's take these nice arrays of these carbon tubes. They actually have little holes down the middle, but that's not important. These tubes are connected by carbon fibers, so they form this porous array in which these dimensions are about 4 nanometers. And let's stuff them with sulfur because the carbon is very conductive and sulfur, again, is a really good insulator. So my graduate student at the time, David G., simply took molten sulfur and imbibed it into the pores. And then when it crystallizes, it forms little spaces in which the electrolyte can gain access. So now we have the sulfur in close contact with these basically carbon wires that are immersed in this melt. And when we then discharge the cell, we form lithium sulfide, which is another really good insulator. But now the lithium sulfide is also in contact with the carbon. So that enables this process to occur relatively reversibly. And so that kind of revitalized some lithium sulfur battery chemistry. There's been something like 2,200 papers published since then. And the problem is the redox shuttle. So here's a nice shuttle, space shuttle. It takes astronauts, I guess, or it's mostly food up to astronauts in the space station. So this is a great process. In the sulfur battery, it is anything but. So in the process of turning the sulfur into lithium sulfide, one goes through soluble intermediates, rather like that hydroperoxy radical or the superoxide radical in the lithium aerosol. A friend of mine at Berkeley calls this a cheese to milk to cheese conversion because this, of course, is a liquid being in solution. So as I mentioned, it has great theoretical capacity. There's been a ton of work done on this. We're getting there. And it turns out, I'll just give you a preview, the problem was the carbon. Still is. So here's how the cell works. Lithium oxidizes from the surface. Electrons are transmitted through the external circuit where they reduce the sulfur and they open up the 8-membered ring to a chain, an S8 chain. The S8 chain then gets reduced further to form S6 and S4, but these soluble polysulfides then diffuse across the porous membrane in the organic electrolyte and of course are reduced in contact with the lithium surface because lithium is more reducing than just about anything. So this is sort of shown in cartoon form here, where the diffusion occurs in the cell. And this effectively has 2 problems. One is that it loses mass because we want that conversion to occur at the positive electrode. We don't want our polysulfides drifting over and self-chemically reducing on the surface because we lose electrons in the process. And then the second problem is that we can build up insulating, thick passivating films on the negative electrode, completely shut down the cell. If we're lucky in the initial stages, they can still be reduced or oxidized back and go back to the positive electrode. But now we're doing chemistry, we're moving electrons back and forth in the cell, and that's effectively a short circuit. So there's many problems. One of them is the loss of sulfur. The other is this redox shuttle, and this is what really has to be mitigated. So we kind of figured this out a few years later. Many other people we're all sort of struggling with this as a community. And the main issue turns out to be that we're all using porous carbons. They have good interaction with sulfur, but they have no interaction with these polar polysulfides or the end product, which is lithium sulfide. And many of us as a community understood this as a group. One of the ways that we learned this was to make in situ cells. We have a capped-in window, so this is basically a coin cell with a window that is transparent to X-rays. And then my postdoc, Marina Cuisinet, and Schwann one of my students took this over to the Advanced Photon Source, and we carried out what we call operando X-ray absorption near-edge spectroscopy. And you don't need to know the details of that. Suffice it to say that this is the discharge curve, this is charge, and this is discharge. So the cell, the operando cell, works just like a regular coin cell, and we're able to collect spectra every 15 minutes and monitor what is actually occurring in this cell as we undergo charge and discharge. And Maureen then patiently fit all of these spectra to known reference materials, and we got a snapshot of what was going on in the cell. And what we learned was that carbon is really inefficient for trapping those sulfides. What is more efficient are polar surface materials. And so the first of these that we worked on was the same metallic oxide that we used for the lithium air cell. We fortunately had it in the lab. And this is, with carbon in one of these lithium sulfur cells, these initial polysulfides that are formed actually desorb from the surface. And because sulfur chemistry is more complicated than oxygen chemistry, suffice it to say that they precipitate Li2S by a disproportionation reaction. And this ends up sort of all over in the cell components, which is exactly where you don't want it, including in the separator. So this is very inefficient for lithium sulfur cells, whereas when we have a polar surface, and this is fortunately metallic and polar, now most of that reaction chemistry occurs rather close to the surface, and we control the deposition of the product, and we also facilitate its oxidation back to sulfur. So since then, there have been a lot of papers. You can see most of these have been published just in the last couple of years. And people now have there was one of these moments, and everyone ran away from carbon, but of course it's difficult to make many of these materials porous. So we've been looking at a range. People have been exploring a lot of polymers. We've looked at oxide, sulfides, and some of these materials, and I'll just briefly tell you how computation, again, can come to the fore. So this is work that's been mostly carried out by Huang and Huang and Xuan Pao. So they're using DFT. This is just pretty canned VASP code, and they're looking at the interaction of a probe molecule, which is lithium disulfide, with surfaces such as carbon, a nitrogen-doped carbon, and a very nitrogen-doped carbon, which is graphitic carbon nitride. And so the molecule is brought down onto the surface in these computations, and we explore what that energy is for bonding and how it bonds. And so we learn, not to our great surprise at this point, there is no specific bonding for carbon, whereas the bonding for the N-doped carbon and the graphitic nitride through a lithium-nitrogen bond is actually very strong. And this just shows the binding energy versus the number, versus this is the number of Li2S2 per supercell. The point is this is 0 carbon, 0 nitrogen, 1 nitrogen, 2 nitrogen, 3, and finally the graphitic carbon nitride. And you can see now that we have pretty strong bonding. And so Xuan and Takudo, one of my other grad students, and Xiao Liang, my postdoc, all got together as a team, and they integrated this carbon nitride with a graphene material, very complicated chemistry, and we are finally able now to achieve very high sulfur loadings in the cell with a very low electrolyte volume, and that, of course, is what we need to do in order to maximize the energy density, and that's just been published in Advanced Energy Materials. So this is work that's almost taken about 2 years to really fully come to fruition. I'll just mention in passing that the other approach is to use electrolytes that are very sparingly soluble for polysulfides, and these include ones in which the organic is actually bound up with the anion and the cation to form these complexes. And because the solvent in these systems is bound up, it can't solubilize the polysulfides because there's no solvent left. So we end up with virtually no solubilization. And how this process really works is still a mystery. We're working on it really right now. This is our initial publication. But the question is whether the sulfur is actually miraculously converting from one solid to another on the surface of the electrode, or whether there is some sparing solubility of the polysulfides. So we call these sparingly soluble systems, and we're very actively trying to find new ones that work really well for this process. So the reason that there isn't a commercial sulfur cell, although there's a couple sort of right on the verge, is that this is really complicated chemistry. And we've summarized it in this article and also in this diagram. So you need a combination of surface chemistry to probe what's going on the surface. You need computation to understand that better. You need to optimize your electrolytes. You need to optimize your cathode architecture because there's a volume change between the product and the reactant. the sulfur and the Li2S. And you also need materials that are simultaneously porous and conductive. So that's a really tall order. And we think that it is achievable, but as I said, it's a work in progress. So I'll just end off with some, moving on beyond lithium ions, some multivalent ions that we've been looking at. And this is work of Xiaoqi and Patrick in my lab. And this shows just how simple these cells are. This is magnesium in an organic electrolyte. So the advantage of multivalent ions is that you can easily use a metallic negative electrode, because effectively magnesium in particular has no there is no dendrite formation. What are dendrites? So in the case of lithium, as you repeatedly deposit and strip lithium, the lithium reacts with the organic electrolyte and it forms these little finger-like dendrites that literally grow from the surface of the electrode. And when they pierce the separator, as they always do, they cause a short circuit and a fire. And this was, for example, the source of the fire in the Dreamliner. And it wasn't because of dendrites, it was because the manufacturers actually had some metal particles in their cell which caused the short circuit. But it can also be caused by these lithium dendrites, and it's why metallic lithium is typically not used. It's not used commercially. But magnesium does not form dendrites. It turns out zinc doesn't if you know how to treat it properly. So this has a real advantage because you go from a very lightweight, fluffy carbon as your negative electrode to something that now has good volumetric density and is reasonably light. And magnesium, of course, is really inexpensive as well. So Xiaoqi made this work with a compound called titanium sulfide, which turns out to be one of the very first lithium-ion battery materials discovered like 30 years ago. So this was kind of cute. The problem and the reason that we used sulfides is that any sort of divalent cation is sticky. And so that gives rise to poor ion mobility in the solid, and that basically means poor power characteristics. So this is sort of a fundamental problem. How do you shield those divalent ions from interaction with a lattice? And in this case, we're using a soft anion sulfur, which is sort of polarizable, and so it's not bad. It kind of works. And the other problem is that the desolvation energy for those multivalent cations is high, because remember, those cations are solvated in the electrolyte, which is this green stuff in the middle. So when they enter the layers or the host lattice itself, they have to shed their clothing of their solvent in order to go into the lattice. And lithium ions do this well. They just love popping into lattices. The desolvation energy penalty is actually pretty low. The magnesium cations are standing around there fully clothed. They're not getting into this hot tub at all. So we fiddled around with electrolytes. We played around with making materials, and we finally discovered this thiospinel, which is also, as you can see, a sulfide. It's got a three-dimensional type structure, same principle. We have very good reversibility in the cell. Cycling capacity stabilization, this is capacity versus cycle number. It's an initial system. We're sort of there. But the point is that we have achieved at least twice the energy capacity of the benchmark system, which was reported in Nature in 2000. And so that's certainly a step forward. But I think what's even really more interesting, at least I think so, is that we collaborated with this group at Berkeley, Gerard Cedar and Kristen Person, to do calculations of the magnesium mobility in this solid. How good is it, or how bad is it? So it turns out, yep, this is a problem. But it also turns out the computation is quite helpful. So here is the lattice itself, and they've calculated two different magnesium contents. That's not important. But the point is that they can calculate an activation energy barrier for the magnesium moving from one lattice site, which is octahedral, through a tetrahedral site, back into its octahedral site as it bumps along. And that value is about 550 millielectron volts. And so my postdoc Patrick Bonnick did some very careful calculations of the diffusion coefficient using electrochemical techniques. And you can then translate these coefficients to an activation energy. And lo and behold, and we didn't make this up, he comes up with almost the same number as theory did. Now, that's good. That means that you can use theory to screen a lot of materials. The bad part is that it's actually faster to do the experiment. His theory calculations took about 2 months. But anyway, beside the point, we actually really appreciate computation. Now this data was collected at 333 degrees Kelvin, and we've compared our results with that of John Goodenough, who did this a long time ago on lithium, and that diffusion coefficient is about a tenth out of lithium, and that was at room temperature. So you can see very easily, and it's exactly the same material that we're using, the thiospinel. So magnesium cations really do move around slowly. There really is an impediment, probably both the salvation energy and the migration. And so Gerard and his group are now working on trying to find materials that have even lower activation energies, and then we're working on trying to make those materials. So in the meantime, instead of beating our heads against that wall, Deepan Kundu and Brian Adams said, well, let's just work with water, and let's work with a layered oxide that has water already between the layers. So now we don't have to shed water molecules as a solvation shell, because the zinc is going from one aqueous medium, this is zinc sulfate in water, to another effectively aqueous medium. And you can't do this with magnesium because it's not stable in water, but zinc is. And so we have developed the first intercalation battery that has interlayer water. The water screens part of the charge of the divalent cation, and it's got all sorts of other wonderful characteristics. Obviously, it's safe, it's environmentally benign, it's really high rate, and it's really stable. This just shows the stability over 200 cycles, completely flat, really good Coulombic efficiency. It's not perfect, but we were pretty excited by this. And part of the reason this works well is that Deepan was able to develop a hydrothermal method of making these long nanoribbons. They're tens of microns long, and they're only about 250 nanometers wide and sort of about 50 nanometers thick. You can see this up in the SCM. So the transport direction is in this direction. So it's only 250 nanometers. And because they're quite thin, think of fettuccine or linguine, it also minimizes the stress of the zinc going in and out of these layers. And because they're also quite hair-like, we can easily form freestanding membranes, which are shown here in a water-based process. So they mat up just like the hair does in your bathtub. And so far we've achieved 1,000 cycles for this cell, again, with very good Coulombic efficiency. And this is just there's probably no electrochemist aside from my group in the audience, but this just shows what we call a rate capability study where a C rate is discharged in 1 hour. And so an 8C rate is discharged in 7.5 minutes. And so you can see that the material still sustains much of its capacity even when we push it really fast, and it comes right back to where we started. So this is all really good news. We have an energy density that's about half that of a lithium-ion cell, which for an aqueous system is really great. And it's low cost and all those good things. And so we're hoping now to start trying to use this for grid storage because of all of these nice characteristics. Okay, so I think that with that I'll stop and just say that the world of electrochemical energy storage has to be integrated, and a view of this is shown here where we have wind storage, we have solar panels both on the roof of homes, we have it in the desert and other places, and that electrical energy is fed into the grid where it then feeds our electric vehicles, which then communicate with the electricity storage in our homes, and finally power the Internet of Things and also things like wearable devices and implantable devices. And that's where we hope to be going in the next 10 years. I mentioned that there's 2 decades from realization to commercialization, and no better example of that is shown by the fact that this group of gentlemen, John Goodenough is a person I mentioned through the talk, he's 94 years old now, and he just achieved he and his group won the Draper Prize, which is kind of the Nobel Prize in Engineering, in 2014. And he developed that technology in 1990. So the take-home message is there really is that gap. And the other is that it really helps to have good genes if you're in this business. Your work may not get realized before you die. But he's still going strong. I just reviewed a paper of his recently. So again, I'd like to thank my research group. They are really the people that do everything. I just kind of sit at my desk. This is a visitor to our group from Japan, Zenpachi Ogumi. And we have a lot of really fine collaborators around the world, some of whom are listed here, and Jonathan Bao at UW. And so with that, I'd like to thank you for your attention.
Linda's going to field her own questions, but I have a little housekeeping item. This event today is being webcast. In order for your questions to be heard, you have to use the microphone. So someone is going to come around with the microphone before you ask your questions. So back to you, Linda.
I'll use that as an inspirational slide.
Well, Linda, I'm happy to start. George suggested that you should consider joining the biology department, and I would endorse that, particularly after hearing your presentation today. For one thing, the fact that you are working on a materials genome, given that genome is a biological word, I think qualifies you for that without any question whatsoever. But one thing that crossed my mind as I was listening to you is this, again from biology. There are two really important membranes, energy transducing membranes in cells. One of them is the mitochondrial inner membrane, and the other is the thylakoid membrane in plants, in chloroplasts, which have evolved the capacity to transduce energy over eons and eons of evolution and have perfected it. One of the membranes takes sunlight energy and converts it into chemical energy. That's the thylakoid membrane. And the other one, the mitochondrial membrane, takes highly reduced chemical energy and releases it in a controlled fashion so it can be captured for reactions. So is there any possibility that there are lessons to be learned from how photosynthesis works and how oxidation works as mediated by thylakoid membranes and mitochondrial membranes respectively? Now I submit, before I turn this back to you, that you probably couldn't drive a Tesla at the speed that it goes with the acceleration it has with biological batteries, if you will. But what about smartphones and related devices?
That's one of those questions where you have to take a deep breath before you answer it. Well, I don't profess to be an expert at those membranes, but I understand a little of how they work, and I think it's an excellent question. I guess my fuzzy-wuzzy answer to that is that the voltages in those membranes are very, very small. So they sort of have they operate by an energy cascade, for example, through cytochromes, which I'm familiar with, through minute little changes in potential, which still are very valuable, but they work in little cascades. And so you not just have the problem of that doesn't happen very quickly, but it also really doesn't give you the voltage that you're going to need to try to drive your cell phone or anything else. You'd have to stack up a lot of systems like that. So it works well as well. It also works well because Mother Nature has had billions of years to perfect the technique. So I guess the question is there anything that we can learn about it? Well, yes. For example, not that we have learned, but when we were struggling with the problems of the superoxide reactivity, we thought about using, there's an example, an enzyme you probably know, superoxide dismutase. And so we actually did look at that to try to figure out how, if there were some things that we could glean from that to help our understanding of the process. But we didn't. So in other words, we looked at it carefully and thought, oh, is there anything we can use from this? So maybe we should be looking at these systems in more detail, not maybe so much for their efficacy, because I said the voltages and the power really are not appropriate for really functional storage, but maybe to get more guidelines about how electrons and ions are moved around in solids, especially with the membranes that are needed in these cells. So I'll take that. I'm not obviously going to be qualified to join the biology department for a while, but I'll work on it a little bit. Ferritin.
Linda, what are the life cycle expectations from these batteries, especially the lithium-ion ones?
The life cycle expectations. Well, that depends on what you define as the end of a life cycle, but typically lithium-ion batteries are considered to be sort of dead when they reach 80% of their capacity. So our zinc-ion battery has a life cycle of 1,000 cycles because that's when it hits 80% capacity. And what we're doing now is obviously figuring out how can we make it last for 4,000 cycles or 5,000 cycles. So the cycle life is very dependent on the kind of system. The cycle life of the lithium-sulfur cell is up to now around 2,000 cycles, but that is under conditions where you don't have a lot of sulfur in the cell. And so then moving that life cycle longer by using high volumetric density cells where there's a lot of sulfur and only a little electrolyte is now the grand challenge. And so we're only at about 250 to 300 cycles for those cells right now. Now, on the other hand, people that have developed solid-state cells, that cycle life can be truly remarkable, 2,000 and 3,000. So there's no one number. It depends on the chemistry that you're looking at. And of course, you're always fighting entropy. There's a question there.
Thank you for a very nice talk. I suspect I, like many other people in the audience, was astounded with the very large number of chemistries and approaches that are being tried, everything from solid state to different electrolytes, kind of confusing. And one question I had was, because there's so much effort being made with different research groups, isn't that leading to perhaps a barrier to adoption of electric cars? Because people are worried, at least I am, that 5 years from now, whatever I buy is obsolete.
Actually, frankly, I'm worried too. Well, I think I can almost guarantee, I shouldn't say that, but I'm pretty sure that in 5 years, the technology that is driving the Tesla is no longer going to be used. But you shouldn't, that's no reason not to buy an electric vehicle, because these batteries, I mean, just because a different kind of technology is developed doesn't mean you can't swap out one battery for the next. So a lot of car manufacturers are turning to licensing the battery pack, not licensing, but basically leasing, that's the word, leasing the battery. And I think part of the reason, one of the concerns is that they don't want people getting a different kind of, not a Tesla, or a Tesla or a Toyota battery, but some other car, some OEM type battery, and then having safety problems because not all batteries are made the same. And so there's all kinds of regulations that are wound up with that. But in principle, that's exactly what you would do. You'd buy a car, you'd lease the battery for a certain period of time, and then when new battery technology comes out, it'll be seamless as far as you're concerned.
Can I just want to follow up with that. I mean, so what you're really saying is that you're pretty convinced that the battery technology in a few years from now is going to be radically or substantially different from today, which means that if somebody's trying to build a battery as part of a system, like a grid system or another system, want to model it, they're going to have to be very agile to keep up with all the changes going on underneath.
Well, I hesitate to say that it would be radically different. We don't have a crystal ball on these things. I think that I think that we're going to have to move to less expensive. There's only two ways to make less expensive batteries for a car. One is the economics of scale, which is where Tesla's going with its gigafactory, and the other is to use less expensive components. And so if anything, I guess the take-home message from today is that, yes, probably what I presented seemed a bit bewildering, but I wanted to give you a kind of a romp through the periodic table and different chemistries, make you appreciate that there are now a lot of things that are being investigated, whereas in the like 10 years ago, everyone was still just doing lithium ion. So we're at this real crossroads now where there's all sorts of different directions to go, and it's not totally clear which is going to be the best. But for example, the solid-state battery that Toyota is developing, and they're solid-state electrolytes, but they use a conventional lithium-ion cathode material. So they're going to have different, of course you're going to have to do battery modeling with those systems, they're different, but they're not going to be fundamentally different than the chemistry we have today. It's just, they're going to be solid-state and not liquid. And the same thing is true for a sulfur cell. So I don't consider those to be, myself, I don't consider those to be impediments. I mean, research catches up pretty quickly with these things. So that's not a reason not to buy an EV now. For EVs.
We've come, I think, to the end of our time. Linda, once again, thank you very kindly.
Okay, thank you for your attention.
Once again, I'd like